Welcome to This Explainer. If you've been staring at pages of electrical engineering textbooks lately, you're probably feeling, a little buried under integral differential equations and complex roots. But today, we're going to bypass all that overwhelming algebra. Instead, we're going to explore how complex electrical systems are actually just seeking a natural, peaceful balance. Okay, let's dive right in.
So let me ask you a quick question. Have you ever tuned a guitar string or maybe ran your finger around the rim of a crystal glass and felt it hum just perfectly? There's this moment where you hit the exact right note and the sound just sustains itself effortlessly. It feels like a really peaceful, natural rhythm. And what's incredibly cool is that the intricate circuits inside our radios, phones, and computers are doing the exact same thing. They're literally just searching for that perfect hum.
Section 1. Meet the RLC components. To understand how our circuits find their rhythm, we first need to meet the players in our orchestra. We're going to treat them as simple, cooperating characters rather than intimidating variables on a chalkboard. It's actually pretty beautiful how simple these components are in their fundamental form. When we categorize them as passive elements, we're talking about the resistor, the inductor, and the capacitor. This just means they don't generate their own power out of nowhere. Instead, they're the elements that either gracefully dissipate or calmly store the energy moving through our system.
Let's look at our very first character, the resistor, denoted by R. Now, the resistor simply dissipates energy, usually as heat. If you think about our circuit as a moving physical system, the resistor provides a steadying, grounding effect. It kind of acts as the calming friction. Without it, energy might just bounce around chaotically forever. It provides the anchor that eventually brings a restless system to a complete stop. Next up, we have the inductor, represented by L. The inductor stores energy in a magnetic field. But its personality is really what matters here. An inductor prefers a smooth, steady current. It naturally resists any sudden, jarring rushes of electricity. If you try to change the current instantly, the inductor pushes back. Think of it like a heavy, spinning flywheel. It takes a bit of effort to get it going, but once it's moving, it wants to keep spinning smoothly, resisting any sudden stops or starts. And finally, we meet the capacitor, or C. A capacitor stores its energy in an electric field. You can characterize the capacitor as a highly flexible element. As voltage pushes into it, it stores up that charge, and when it gets full, it pushes back, smoothly and rhythmically, releasing that gathered charge right back into the circuit. It acts very much like a gentle spring in our mechanical analogy.
Section 2. The push and pull. Now that we know our characters, the anchor, the heavy wheel, and the spring, let's observe how the inductor and capacitor interact in a delicate, continuous dance of energy.
So the absolutely crucial point here is how these two elements, inductors and capacitors, behave as complete opposites. Over time, in a steady state, inductors act like short circuits, happily letting constant current flow through while resisting any sudden changes. Capacitors, on the other hand, eventually act as open circuits to steady voltage, blocking constant flow, but they eagerly absorb sudden changes. One loves steady flow, the other loves to store up pressure. When you put them together, they create this beautiful push and pull dynamic, passing energy back and forth from the magnetic field of the inductor to the electric field of the capacitor.
Section 3. Finding resonant frequency. We are now ready to see what happens when these opposite, complementary forces find their perfect point of equilibrium. This is where the magic really happens.
When we wire these components together in a series RLC loop, you might instantly picture those intimidating integral differential equations from Kirchhoff's voltage law. But honestly, don't worry about that right now. I want to reassure you that those equations are really just a mathematical way of describing energy peacefully bouncing back and forth. The current flows out of the capacitor, builds momentum in the inductor, gets slowed by the resistor, and then pushes back the other way. It's just a pendulum swinging.
Let's see how this builds into something genuinely elegant. We can actually break down that daunting quadratic equation into 3 really calm steps. First, the circuit is given some energy, and its natural state is just to let that energy slosh around. Second, the inductor and capacitor negotiate a balance between momentum and springiness. Third, they lock into a specific rhythm where they perfectly match each other's pace. That rhythm is the resonant frequency, often written as omega naught equals 1 over the square root of L times C. It's incredibly simple. It's just the pure, natural heartbeat of those two components combined.
When we look at the roots of the characteristic equation, notice case 3. The textbook literally calls this out as being of great importance, and it's the underdamped case. This is the specific state where the resistance is low enough that the energy doesn't just die out immediately. Instead, the roots are complex conjugates, meaning the energy oscillates smoothly. It fades gently over time because of the resistor, but it rings out first. This underdamped state is exactly where the magic of resonance lives.
Section 4. Resonance in real life. So we've got the math down, but let's explore how this mathematical harmony isn't just for passing exams. It is actively and practically harnessed in the real world all around us.
I absolutely love this textbook insight. Electrical resonance isn't just some abstract concept. It is literally the exact same physical phenomenon found in a vibrating stringed instrument. Just as a guitar string vibrates at a specific frequency based on its tension and mass, an RLC circuit resonates at a specific electrical frequency based on its inductance and capacitance. The math is identical. The physics are identical. The circuit is quite literally singing.
And this is exactly how engineers use this balance to tune into specific frequencies out in the real world. By designing circuits that resonate at a specific pitch, they create pass bands that allow clear, desired signals to flow through, kind of like picking out your favorite radio station. At the exact same time, they create stop bands that calmly filter out the chaotic noise of everything else. It's all about tuning into natural rhythms to find the signal hidden in the noise.
Section 5. A peaceful closing thought. Let's bring this explainer to a gentle close by reflecting on the broader, more comforting meaning of this physical principle.
Whenever you're faced with an intimidating engineering problem, or, a page totally full of dense formulas, just remember what's actually happening underneath it all. Behind every complex system is a natural frequency waiting to be found. Everything, from a guitar string to a highly sophisticated RLC circuit, ultimately seeks its own natural, harmonious balance. So the next time you hold a piece of modern technology, ask yourself, what invisible resonant frequencies is it quietly singing to right now? Keep exploring, keep learning, and I'll see you in the next explainer.